Okay, hey, we're recording. What we're going to do today is we're going to look at rate in and rate out problems, and this is going to be an application of the integrals. And the AP people, and these are strictly AP problems. You won't probably find any of these problems in the textbook, but the AP people decided to put these on the exam. And of the free response questions, you're probably going to see one that's going to be a rate in and rate out problem. And I'll kind of give you the overview of what's going to happen here. It's going to be analogous to if we had a velocity versus time curve, and we had the function, and we found this area right here. And if it's above the x-axis, that's going to be the total distance traveled. And the thing I want to concentrate on here is look at if this was meters per second and this time was in seconds. And if we multiplied the units together, you have meters per second times seconds, and the seconds will cancel out, and you're just left with meters, which is going to be the distance that you traveled, which kind of makes sense. But what we're going to do when we're doing rate in and rate out problems, instead of being a velocity versus time graph, what it will be a time here. And instead of being meters per second or miles per hour or something of that nature, it's going to be something like people per hour. And we might have let's see, cars per minute. We may have fishes per hour or fish per hour. And these units here are going to correspond with these units here. So for an example, if we had, like let's say we had people per hour, and we had the time here of being hours, and we looked at the area underneath the curve, if you multiply the units together, this is going to be the number of people. Does that make sense? Just like on this one, when you multiply the units, this unit's going to be in meters. Okay, now on these rate in and rate out problems, here's what the bigger picture of it's going to look like. You're going to look at this thing is, let's say you have this barrel here, or this bowl, or whatever you want to call it, and you're going to have stuff going in, and it comes down here, and you're going to have stuff going out. And this is going to be your rate in, and this is going to be your rate out. Now this rate in, if you look at the units, it's going to be people per hour, cars per minute, fishes per hour, whatever the unit is, gallons per day, and this units on this is going to be the exact same thing. So this may be, for an example, people per hour, and what's going to come out is going to be the exact same units, people per hour. Okay, now I'm going to define A of t is the amount in the, we'll call it a bucket, at any time t. Okay, and so we're going to have a starting point here, and let's say that at time t equals 0, at t equals 0, there is B amount in there, B amount in the bucket. So if I want to find what A of t is, and this is the thing that you're going to have to do with every single problem, but it's just going to be for your benefit. Just like when we did justification, when we do line justification, and you have A and B, and you have positive here, and you have negative here, and positive here, positive, negative, positive. You have a local max here and a min here. This is just for your benefit. You're not, the AP people aren't going to give you any credit for this. All right. So this, defining A of t in these problems, is just going to be for your benefit. Sometimes they may ask for it, and sometimes they won't. But what we're going to do is we're going to start off with A of t. So that's going to be the amount at any time t. And at time t equals 0, there's going to be B amount in there. Now what I'm going to do is, would you agree that as the rate's going in, would you agree that if there's more going in than coming out, this level is going to be rising? And if there's more going out than coming in, this level is going to be falling. So this is just like you're in a bathtub and you turn the water on and then you pull the plug out. Well, there's really no sense in doing that, but that's the kind of the analogy of doing that. If more's going in than coming out, then it's going to be filling up. If more's going out than filling in. But if they're exactly the same, that means it's going to be it's not going to be rising or falling. So anyway, A of t is going to be the amount that you start with, which is B, plus, now we're going to have to add all the stuff that goes in here. And what I'm going to define as the stuff going in there is I of x. That's going to be the amount that goes in. That's your rate that's going in. So I'm going to add all the stuff that goes in. So I'm going to integrate from 0 to t of I of x dx minus the stuff that comes out. And the stuff that comes out at that rate I'm going to define as O of t. And I'm going to subtract the integral from 0 to t of O of t dt. So this formula right here is going to be the amount at any time t. So if I said I want to know how much is in there at time 7, I just have to plug the 7 in here, and whatever we started with, I'm going to integrate from 0 to 7 and then subtract the integral from 0 to 7. That makes sense? Okay. Now another couple other things, and I know we're just dealing with abstract, and we'll look at a specific example. We'll actually look at a whole bunch of specific examples here in just a minute. But let's go ahead and define this stuff here. This right here is the amount going in at time t. And this, what do you think this is? The amount, what? Going out. At time t. And what's this B value? That's your starting. I guess I'll say it's a starting point. Now they're going to ask several questions about this, and one of the questions they're going to say is the amount increasing or decreasing. Now I see the words increasing or decreasing, so I want to know if this amount is increasing or decreasing. So what do we have to do? Well, when we see the word increasing or decreasing, or they might say max or min, you're going to have to take the derivative of this and set it equal to 0. So if I were to take the derivative of this, I would get a prime of t is equal to, well, what's the derivative of this number here? This b value. That's a constant, so that's going to be 0. Plus, what's the derivative of this integral here? Well, that's the second fundamental theorem of calculus. You just take the t and plug in here. So we're going to have what? I of t minus O of t, right? We've got to take the derivative of that. And what do we got to do with this thing? Set it equal to 0. So now what this is going to tell us to do is if we set this equal to 0, this will imply that I of t, the rate going in, is going to equal to the rate going out. And we'll look at example, and I know this is abstract and you may think, well, what the heck's going on? But for right now, just kind of play along. Now, not only increasing or decreasing, they may see the maximum amount or minimum amount. So if we see the maximum, we're going to use this thing. We're going to set a prime of t is equal to 0. So if you want max or min, set I of t equal to O of t and solve for t. And we'll say this is t1 and t2. And this was where a prime of t. And you may have to plug numbers in here, positive, negative, positive, let's say. And then you can determine where you have a max and min. Alright, I know it seems kind of abstract, and let's go ahead and kind of look at an example now. Okay. Hang on just a second. Let me turn this off.